Hello students, welcome to physics class. Today we discuss resolution of a vector. Let us see what do you mean by resolution of a vector. It's a process of splitting a vector into two or more vectors in such a way that their combined effect is same as that of given vector. The vector into which the given vector is resolved are called the component vectors. It is a process of splitting a vector into two or more vectors in such a way that their combined effect is same as of the given vector. The vectors into which the given vector is splitted are called component vectors. Here we have a vector R which result in terms of vector A and vector B. Here vector R, vector A and vector B lie in the same plane. Now we are going to write this vector R in terms of two other vector A and B. For that we have vector R. Vector R is equal to vector OQ. That is the tail of vector R is O and the head of vector R is Q. From the head or from the tail of vector R, we are drawing another vector, say OP, which is parallel to vector A. We are drawing vector OP, which is parallel to vector A, and which is equal to m into A. M is a scalar quantity, a number. If a vector A is multiplied by m, it becomes vector m into A. We know that a vector can be multiplied by a scalar or a number. Then its magnitude is increases by m times. If m is a positive number, m times it increases, m into A. The direction is not changed because m is positive. Now, vector MA, vector OP is equal to what? Vector OP is equal to m into A. M into A. The direction of A and MA is same. Now, from the head of vector OP, we are drawing another vector, say vector PQ. Vector PQ is drawn, and vector PQ is nothing but n into B. Vector B into n. N is another positive number. So the direction remains same, but magnitude is n times of B. Now, if you are applying the triangle law of vector addition, we can write as vector OQ. Vector OQ is equal to vector OP plus vector PQ. Vector OP plus vector PQ is equal to vector OQ. OQ is equal to vector OP plus PQ. What is OP? OP is equal to m times of vector A. What is PQ? N times of vector B. So we can write as vector R is equal to MA plus NB. Vector R is equal to vector MA plus vector NB. Now we resolve this vector R in the direction of vector A and vector B. Now we resolve the vector R in the direction of two other vector, in the direction of vector A and vector B. Now we call this m into A is the m into A and n into B are the component of vector R. The vector m into A and n into B are known as what? The component vector. The component of vector R in the direction of A and B. The vector m into vector MA is the component of vector R along vector A. NB is the component of vector R along the direction of vector B. And together we calling as they are the component vectors. Vector MA and vector NB are components of vector R. Here MA is the component along the direction of A and NB is the component along the direction of B. Now we write the vector R as the sum of two other vectors. Any vector can be written so. And this process is known as resolution of a vector. Actually, it's a splitting. We have split the vector R into two vectors and write the sum of two vectors. And that two vectors are known as the component of the given vector. So that's the process of resolution of a vector. Now see another concept, the orthogonal triad of unit vectors. Orthogonal triad of unit vector. We already know what is a unit vector. Now see what are orthogonal triad of unit vector. In a right-handed Cartesian coordinate system, the three vectors I, j, k, the three unit vector I, j, k are used to represent x, y and z axis respectively. The positive direction of x, y and z axis respectively. Here vector I, a unit vector drawn along the direction of x axis, vector j, a unit vector drawn along the positive y axis, and vector k is drawn along positive z axis. So I, j, k are used to represent positive x, y, z axis respectively. Okay, these three mutually perpendicular unit vector I, j, k are collectively called orthogonal triads of unit vector. They are the three unit vector along the positive direction of x, y and z axis. Why we introduce this orthogonal triad of unit vector? In order to resolve a vector into mutually perpendicular direction. Actually this time we resolve the vector into in the direction of two other vectors a and b. A and b are not perpendicular to each other. If we are using this concept of orthogonal triads of unit vector, we can resolve a given vector into along x, y and z axis by using this three unit vector I, j, k. They are collectively known as orthogonal triads of unit vector. Now let us see what are the rectangular components of a vector. The rectangular component of a vector means when a vector is resolved along two mutually perpendicular directions, the components so obtained are called the rectangular component of given vector. It means when we resolve a vector along two mutually perpendicular directions, the components so obtained are called the rectangular component of the given vector. For example, here we have vector A, OP, vector OP is equal to vector OP is equal to vector A. The head of the vector is P and tail of the vector is O. This is drawn here. The vector A is shown here. Now we are going to resolve this vector into two mutually perpendicular directions. For that, from the tail of the vector A, that is from O, we drawing two axes, that is x and y axis, that is OX and OY. Here the angle between OX and OY is 90 degree, that is two OX and OY are mutually perpendicular. Then from the head of the vector OP, we are drawing two perpendicular, one to x axis and other to y axis, that is PM to x axis and PN to the y axis. PM and PN drawn perpendicular to x and y axis respectively. Now this OM having a magnitude of AX, OM having vector OM having a magnitude of AX and vector ON having a magnitude of AY. We can treat them as a vector because they have a magnitude AX and a direction is taken along x axis. ON having a magnitude AY and direction is taken along y axis. So they are vector. OM, vector OM magnitude is AX, vector ON magnitude is AY. Or AX and AY are the vectors. AX and AY are vector. They are mutually perpendicular to each other. Now, by parallelogram law of vector addition, if you are applying parallelogram law of vector addition here, we can write vector OP is equal to vector OM plus vector ON. Vector OM plus vector ON. Or vector A. Vector OP is equal to what? Vector A and vector OM is equal to vector AX and vector ON is equal to vector AY, or A equal to AX plus AY, vector A equal to vector AX plus vector AY. Now we can see the vector Ax and vector Ay are perpendicular to each other, and vector Ax is known as horizontal component of vector A. The vector Ax is known as what? Horizontal component of vector A. And vector Ay is known as vertical component of vector A. Now we find the horizontal and vertical component of vector A. The horizontal component is what? The horizontal component is vector Ax and the vertical component is Ay. By using this vector Ax and Ay, we can write vector A. So we resolve this vector A into vector Ax and vector Ay. Vector A is written as the sum of two other vectors, Ax and Ay. Ax plus Ay is equal to vector A. Now, see, how can you write this horizontal component, the magnitude of horizontal component? For that, if I and j be the unit vector along x and y axis respectively, and ax and ay be the scalar magnitude of vector A. Ax and ay be the scalar magnitude of vector Ax and Ay respectively. Now we can write as vector Ax is equal to Ax, magnitude of vector Ax into I, and Ay is equal to magnitude of vector Ay into j, because I and j are the unit vector along Ax and Ay. So we can write this vector Ax is equal to magnitude of Ax into I, because I is a unit vector along Ax. And vector Ay can also write as vector Ay is equal to what? Vector Ay is equal to Ay, magnitude of Ay into j, because j is a unity vector along Ay. So if you want, we can write the vector A is equal to Axi plus Ayj. Vector A is equal to what? Axi plus Ayj. Okay. Now, if vector A makes an angle theta with x-axis, here in this diagram shown that vector A makes an angle theta along x-axis. So how can you write this Ax? Okay, from the trigonometric relation, we know that if you are finding cos theta from here, what is cos theta? Cos theta is equal to Ax by A. Cos theta is equal to Ax by A. So that is Ax is equal to, you can write as Ax is equal to A cos theta. Cos theta. Ax is equal to A cos theta. Similarly, what is sine theta? From this triangle, what is sine theta? Sine theta is equal to opposite side. Opposite side is actually Ay. Ay. This is also Ay, isn't it? Ay by A. Or Ay is equal to what? Ay is equal to A sine theta. Ay is equal to A sine theta. So we can write this Ax is equal to A cos theta, Ay is equal to A sin theta. That are the magnitude of vector Ax and Ay. Ax is equal to A cos theta, Ay is equal to A sin theta. This is the magnitude of horizontal component, and this is the magnitude of vertical component. Now see the relation between them. What is the relation between the horizontal and the vertical component? The square of horizontal component plus the square of vertical component. Ax square plus Ay square. That is equal to A square cos square theta plus sin square theta. Because you know Ax is equal to A cos theta, Ay is equal to A sin theta. So Ax square, A square cos square theta, Ay square, A square sin square theta. Add them. That is, we are keeping A square outside this bracket. A square into cos square theta plus sin square theta. That is Ax square plus Ay square is equal to A square, because cos square theta plus sin square theta is 1. Or A equal to magnitude of this vector A is equal to root of Ax square plus Ay square. Now by using the magnitude of this horizontal and vertical component, we can write the magnitude of vector A like this. A is equal to root of Ax square plus Ay square. Now see the here angle theta. So we can write tan theta is equal to ay by ax tan theta, or theta is equal to tan inverse of ay by ax. Theta is equal to tan inverse of ay by ax. That is the rectangular component of a vector. The rectangular component means the two mutually perpendicular vectors. The rectangular component of a vector means two mutually perpendicular vector. Here the vector A, right, in terms of two other vector ax and ay. Ax and ay is mutually perpendicular to each other. So we write A is equal to ax plus ay. Ax plus ay. Okay. Now in another term, by using the unit vector, we can write as vector ax is equal to axi. Vector ay is equal to ayj. I and j are the unit vector along x and y axis. So vector A can also write as axi plus ayj. Axi plus ayj. What is ax? Ax is the horizontal component. What is ay? The vertical component. Ax is equal to a cos theta and ay is equal to a sin theta. That are the magnitude of horizontal and vertical components. Now let us see how can we resolve the position vector into rectangular component. We know that position vector is a vector which gives the position of an object with respect to the origin of a coordinate system is called position vector. A vector which gives position of an object with respect to the origin of a coordinate system is called position vector. Actually, a position vector tells the straight line distance to the object from the origin, and it tells the direction of object with respect to the origin. A position vector always tells the straight line distance of the object from the origin, and it tells the direction of object with respect to the origin. Here we shown a position vector r. Here the position of the object is p. X and y are the coordinates. X and y are the coordinate with respect to the origin. Okay, now we can write this position vector as, if you are resolving this position vector r into rectangular component, for that first draw the pm, which is perpendicular to x axis, and pn perpendicular to y axis. Let us say OM, vector OM is equal to vector xi, and vector ON is equal to vector yj. Vector xi and yj are perpendicular to each other. Now, by the resolution of vector, we can write vector r in terms of vector xi and yj. By parallelogram law of vector addition, we know that OP is equal to OM plus ON. Vector OP is equal to vector OM plus vector ON. But you know that vector OM is xi and vector ON is equal to yj. So the position vector can write as r is equal to xi plus yj. R is equal to xi plus yj. Xi is the x component or horizontal component of position vector. Yj is a vertical component of position vector. Xi and yj are mutually perpendicular to each other. Or the magnitude of this position vector can write as r is equal to root of x square plus y square. Also we can write x is equal to r cos theta and y is equal to r sin theta, which we already discussed. X is equal to r cos theta and y is equal to r sin theta. So this position vector is resolved into rectangular component xi and yj. So we can write the position vector r is equal to xi plus yj. Now position vector is nothing but is a vector which gives the position of an object with reference to the origin of coordinate system, and it tells the straight line distance of the object from the origin, and it tells the direction of object with respect to the origin. And by using the rectangular component, we can write the position vector r is equal to xi plus yj. But this position vector is now in 2 dimensions. Suppose if the object is moving in 3 dimension, the object is moving through a space. So we have to use the 3 coordinate. Here we use only 2 coordinate, x coordinate and y coordinate. Now suppose if the object is moving in space, we can use all the coordinate x, y and z. For that, suppose the object is moving in 3 dimension. This is the position of the object at that instant. Let's say x, y and z are the coordinates. X, y, z coordinate. Ax, ay and az are the vector along x, y and z axis respectively. The component along x axis is ax, the component along y axis is ay, and component along z axis is az. Now we can write this vector A is equal to ax, ay plus az. Vector A is equal to ax plus ay plus az. Or vector A is equal to axi plus ayj plus azk. Now this vector A is resolved into 3 mutually perpendicular vector. One is along x-axis, another is along y-axis and z-axis. Ax, ay, az. Axi, ayj and azk are the x, y and z component of this vector. Now we can write the magnitude of this vector A is equal to root of ax square plus ay square plus az square. Now if you are using this concept in case of position vector, we can write this position vector with one more component, that's vector r is equal to xi plus yj plus zk. If the object is in 3 dimension, we can write this rectangular component of the vector position vector as r is equal to xi plus yj plus zk. We have 3 component, x component, y component and z component. For example, if the coordinates of a point are 3, 2 and 1. The x coordinate is 3, y coordinate is 2 and z coordinate is 1. How can you write the position vector of the object? The position vector of the object can be write as 3i plus 2j plus 1k. That's the position vector of the object. Because x coordinate is 3, y coordinate is 2 and z coordinate is 1. Another example, if the coordinates of an object are 2, 1 and 3. X coordinate is 2, y coordinate is 1 and z coordinate is 3. What is the position vector of that object? The position vector of the object is equal to 2i plus 1j and 3k. This is the position vector of the object. Now in this way, we can write the position vector of an object. That's all today. Thank you.